Hi everyone, it's science time and today we will be talking about the spring constant K and the length of the spring related to Hooke's law part number 2 IGCSE course. So before going through this video, I will be asking you to subscribe my channel. Don't forget to like, drop a comment, any suggestions, any improvements. Feel free to ask any educational questions that came to your mind. So let's do this. So now a quick revision from part number 1. So I will strongly recommend everyone checking out and watching my last video, part number 1, since it is pretty much really important. And why it is really important? Because the basic and the fundamental informations are composed in that specific video in part number 1. So for comprehending the concept in this presentation, you will need to check out my last video, because also a question in the last slides of the same presentation, of this presentation, is related to the last part also. So the spring constant shows the stiffness of the spring and how hard it can be stretched, which is something constant for each type of spring. Don't forget this. The spring constant, the K of each spring, is not going to be changed unless its length is going to be different, like we are going to cut it in different pieces. In that case, the K will be different. That we are going to talk about it in details in the next slides. For instance, when the K of a spring is 500 Newton per meters, or in other words, kilogram per centimeter second squared, defines that when 500 newtons is being applied, is being hanged on a specific spring, the extension, the x, will be 1 meters. So for comprehending this concept in a much more organized way, let's consider that the loads in the right picture, which is known as N, is heavier than the loads in the left picture. So in that case, as you can see, there are springs that nothing is being hanged on it. That means the extension is 0. And then N is being hanged on that spring. Let's consider that like these two springs are totally different, with different spring constants. So when they are hanging N on the right picture to that spring, the extension will be X. But on the other side, in the left picture, when like the load which has a less weight, a less mass, a less load compared to N is being applied to the spring in the left picture, the extension will be the same. It will be X, because it says X, as you can see. So in that case, let's say when two different springs, two different loads is being applied to it, their extension is the same. So indeed, when the heavier one is being applied to that spring in the right picture, and its extension is the same as when a mass or a load with less mass is being applied to another spring, another type of spring with different spring constants in the left picture, and the extension is the same, this means that the spring in the right picture is its stiffness is much higher. And why? Since when like a heavier load, a heavier mass is being hanged on it, it's going to have the same extension. So it's much more stiffer compared to the spring in the left picture. So, and now the proportionality between the length of the spring and the spring constant K. The spring constant, or let's say K, and the length of the spring are inversely proportional, which defines that as the length of the spring decreases, as I also talked about it in the last slide, its K is going to increase. For instance, the spring constant of a spring is K. let's consider it that the spring constant is K, a number, no difference. Let's say K. When we cut the same spring into two equal pieces, the spring constant of each will be 2K. Look at this. So now the spring constant of that spring, like the spring was 1 meters, like its length was 1 meter. It was K. And now when we are going to cut it in two equal pieces, it becomes 50 centimeter. So in that case, the spring constant of each of those tiny springs are 2K. So as the spring constant decreases, as the length of the spring decreases, the spring constant increases. That means when the length, in this case, in this example, when the length of the spring is cut into half, into two equal pieces, that means it is halved, the spring constant will be doubled. So, and now different amounts of K when placed in different positions. This is the main and the most important slide in this video, in this presentation. When we place two or more different springs with different spring constants beside each other and then hanging both on a single load, let's consider that we are placing two different springs beside each other and then hanging both of those springs on a single load. That means that load is being hanged on both of those springs. In that case, the K will be added. It's not going to be multiplied and like no other strange and unconventional things. It will be added. The springs are parallel. So in the case that those springs are parallel, in that case this statement will be true. The K, like K1 and K2 in this case, will be added if you want to calculate the spring constant of these two in one number indeed. But if, pay attention, but if we put those different springs, two or more, no difference, hanging on each other, not beside each other, hanging on each other on a vertical line, as you can see in the picture, in the left picture, and then hanging a load on them for calculating the total spring constants, there is a formula shown as below. For instance, if there are three springs hanged on each other, 1 over K is the answer. 1 over K equivalent to 1 over K1 plus 1 over K2 plus 1 over K3. No difference how many springs. If it's two springs, in that case, 1 over K equivalent to 1 over K1 plus 1 over K2. It's really important. So different positions are going to make changes for calculating the spring constant. As you can see in the picture, in B, or let's say in the right picture, those two different springs are being placed beside each other. So if you want to calculate the spring constant and write it as a single whole number, indeed, they will be added. The spring constants will be added. But in A, in the left picture, they are not going to be added anymore. They are not going to be divided anymore, and no strange things. There is a formula for it, that for calculating the spring constant in a single number, in a single whole number, the formula will be 1 over K equivalent to as many as springs which are being used, 1 over K1 plus 1 over K2, and so on, if there are more springs being used in that investigation. And now, for comprehending the aspect in a much more specialized way, I will be improving that this statement about different positions, in this case, when we are putting those springs on each other in a vertical line, is true, that formula. For instance, we cut a spring, so they don't have different spring constants, into two equal pieces. So now the spring constant of each is equivalent by 2K, as we talked about in the last slides. That when the length is being halved, the spring constant of each tiny pieces will be doubled. So 2K for each. When they are hanged on each other on a vertical line, so on a vertical line, it's not they are going to be placed beside each other on a parallel line, not that. They are going to be hanged on each other on a vertical line. It's exactly the same as when they weren't cut yet. So let me read it again. It's really important. When they are hanged on each other on a vertical line is exactly the same as when they weren't cut yet. Don't forget this. That means when we are cutting, like no difference when we are cutting a spring into two pieces and then putting those two pieces on each other is exactly the same thing, exactly the same spring constant. And I want to improve this. So my final answer must be K equivalent to K. Therefore, based on the information given to us, and also the formula 1 over K equivalent to 1 over K1 plus 1 over K2, and not so on, because there are two pieces that are being used in this investigation. K1 and K2 are the pieces with the K of 2K, with the spring constant of 2K. So 1 over K equivalent to 2 over 2K. And why? Because as you can see in the right hand side of the formula, so let's put the information that we know in the formula. So K1, its spring constant is 2K. So let's put 1 over 2K plus 1 over 2K, because K2 also has the spring constant of 2K. So 1 over 2K plus 1 over 2K equivalent to 2 over 2K. And now cross multiplication, we are going to get 2K equivalent to 2K, and then simplification, K equivalent to K, when we are dividing both sides by 2. So we noted that the answers will be the same. Their spring constants, the K's will be exactly the same. And now let's go through a couple of questions that might help us in this concept. What is the relationship between the spring constant K and the length of the spring? Choice number 1, proportional. Choice number 2, inversely proportional. Choice number 3, no relationship. Choice number 1, no idea. Yeah, I think it is going to be choice number 4. Okay, so pause the video and think about it. So, answer to question number 1. What is the relationship between the spring constant K and the length of the spring? So based on the informations given to us, we said that as the length of the spring is going to be, for instance, halved, the spring constant will be doubled, and exactly the same when the direction is going to be reversed. When the spring constant, the K, is going to be halved, which is something really impossible, when the spring constant of a spring is going to be halved, its length must be increased, must be doubled. So the answer will be choice number 2. Since as the length of the spring is cut into two equal pieces, or into different equal pieces, the stiffness K of each of those springs will be more compared to the same spring which hasn't been cut yet. So, question number 2, it is extended. So, if you didn't understand, if you didn't comprehend, if you weren't be able to answer this question properly, you can rewatch my video again, and also you can refer on part number 1. Don't forget this. So 3 different springs are hanged on each other with the spring constants including 200, 300, and 400. A load is hanged on those springs which its mass is 30 kilogram. What is the extension? So this question, it was the same question that I said we have to refer on part number 1. So until now, if you haven't seen, if you haven't watched part number 1, after watching this video, please, I would strongly recommend watching my last video, part number 1, and then you will be able to answer this question just like a piece of cake. Choice number 1, 0.33 meters. Choice number 2, 2.76 meters. Choice number 3, 3.26 meters. Choice number 4, none. So as you can see in the picture, so the given information, there's a roof, 3 different springs with different spring constants are being hanged on each other on a vertical line that a mass, like a load with a mass of 30 kilograms, is being hanged on it. So answer the question number 2. So guys, the answer will be choice number 3, since based on the formula 1 over k equivalent to 1, in this case 3 springs, so 1 over k1 plus 1 over k2 plus 1 over k3. So k1, as we know, it is 200, it's spring constant, I mean. K2 it is 300 and K3 it is 400. So in that case, after placing those things beside each other, 1 over 1 over 200 plus 1 over 300 plus 1 over 400, after determining the denominator, we notice that the answer will be 13 over 1200. So therefore, 1 over k will be equivalent to 13 over 1200. And that's not the final answer. That's not the final step. So at first, cross multiplication. So we notice that 13k equivalent to 1200. So k, it is approximately equivalent to 92 Newton per meters. So based on the formula that you have to refer on part number 1, F equivalent to kx, force equivalent to spring constant times the extension. Force is equivalent to the weight of that load because it is being placed on earth. So in that case, force equivalent to 30 being multiplied by 10, as it is written in the base form of the question, gravity equivalent to 10 meter per second squared, so 300 Newton. And K, as we know, as we noted, as we solved, it is 92 Newton per meters. So we want the x. So for calculating the x, after putting the x in the subject of the formula and putting f in the other side, in that case, it will be f over k equivalent to x, the extension. So in that case, 300 divided by 92 equivalent to 3.26 meters in 2 decimal places. So guys, that's all for today. Don't forget to subscribe, like, and share. And please check out my last video related to the same formula, Hooke's law, part number 1. So feel free to ask educational questions that came to your mind. So see you in our next video.